X-rays. X-rays are electromagnetic radiation whose wavelengths are of order of 1 angstrom. 1 angstrom is about 10 to the minus 10 meter. Compare this with a wavelength 550 nanometer, 5.5 times 10 to the minus 7 meter, at the center of the visible spectrum. The standard optical diffraction grating cannot be used to distinguish between the different wavelengths in the X-ray wavelength range. Why? Now check. This angle, the first order for the X-ray. This is the one. This is X-ray 1 10 to minus 10. This D is around this one. D is around 10 to the minus 6 order, as usual. We put this one, we found this theta is so small, you cannot tell it. So what we do, we need to find some grating with D is approximately equal to the wavelengths. Well, where to find it? Where to find it? Let's see how X-ray was emitted. This is the heat, okay, resistance. We apply a current, so it will have a current, it getting heater, and an electron inside escape from it. Once it escapes from to the space, there is a huge voltage applied. So this is positive, so the electron with X-ray hit the positive, okay, and this is a metal tungsten. And that when electron hit the tungsten, a tungsten will elect X-rays. X-rays are produced when the electron escape from the heated filament F, are accelerated by potential difference V, this potential V, and strike a metal target T, and the tungsten emitted X-ray. In 1912, it occurs to German physicist Max von Laue that a crystalline solid, which consists of a regular array of atoms, might form a natural three-dimensional diffraction gratings for X-rays. This is sodium chloride crystal. Okay, the idea is that in a crystal such as sodium chloride, a basic unit of atom, we call it unit cell, repeats itself throughout the array. This is a unit cell of sodium chloride, the salt. Okay. In sodium chloride, this is the unit cell. You have 4 sodium ions and the 4 chloride ions are associated with. Okay. So this is the picture section of soda crystal, sodium chloride, and identify this basic unit. This is the basic unit. Okay. The basic unit cell is the cubic measuring A0 on each side. And you will have question. You see, there's so many atoms in each unit cell. How come you see only 4 sodium ions and 4 chloride ions? Now, when we analyze, we find this chloride is on the corner. So this atom is shared by 8 unit cells. It's a corner, you have 8 shared. And so only 1/8 of this chloride belong to this one. And this chloride is on the face. It shares with another one. So only half belong to it. So we put this together, you will find only 4 chloride and 4 sodiums included in this unit cell. This is a Max von Laue from Germany. Although the procedure of diffraction of X-rays by a crystal is complicated, the maximum turns out to be directed as if the X-ray were reflected by a family of parallel reflecting plates. Okay. or we call crystal planes, that extend so the atom, you have atom on that one, within the crystal, and that contains regular arrays of the atom. The X-rays are not actually reflected. We use these frictional planes only to simplify the analysis of the actual diffraction process. Bragg's law. We define the theta are defined relative to the surface of the reflecting plane rather than to a normal one in this case, okay? D is the interplate spacing, okay? We looked at the line reflect from this family of planes, okay? They are in phase when it is shining in, and they are out of phase outside. If you want to see them, they should be in phase too. But the question is, they have path difference. Okay, these two lines, when larger than this one, there's two green lines. Okay, to have a constructive interference in the beam diffracted in the direction theta form the entire family of planes. This one. The rays from the separation planes must reinforce each other. In other words, the distance difference, 2d sine theta, must be an integral number of wavelengths, so they can be in phase too. Okay, look at this. This is perpendicular, this perpendicular. So this angle equal to this angle, and this, the green line is equal to d sine theta. You have 2d sine theta is the path difference between these two. Okay. It must be equal to m lambda, so it can be constructive interference. The edge length A0 of a unit cell can be related to the interplane space D of the family of planes. Well, it's complicated. I'm not going to do it here. Okay. Regardless of the angle at which X-rays enter a crystal, there's always a family of planes from which they can be said to be reflected, so that we can apply Bragg's law. X-ray diffraction is a powerful tool for studying both X-ray spectra and the arrangement of the atoms in crystals. To study spectra, a particular set of crystal planes having a known spacing d is chosen. Diffraction from these planes diffracts different wavelengths at different angles. I detect them that can discriminate one angle from another can be used to determine the wavelengths of radiation reaching it. On the other hand, we can study the crystal itself using a monochromatic X-ray beam, determining not only the spacing of the various crystal planes, but also the structure of the unit cell. This is Bragg, okay? He won Nobel Prize in Physics in 1915. The DNA molecules and many other equal complex structures have been mapped by X-ray diffraction.